What we're talking about now is Lewis structure. How do we represent those bonds? How can we draw things instead of having to do our H and our Cl with these pictograms and circles? How can we just say H, we already started doing this, or I already started doing it, H bond Cl. I keep standing in front of it. How do I know I'm referencing a bond here? Is that an arrow? I know it looks like an arrow. Give me a little, fine. How do I know I have a bond connecting the hydrogen and the chlorine? I am defining a drawing. And I'm defining that a line represents the bond. And if I don't have that line there, I don't have a bond. Right? So we're now adding drawing rules to explain how we would draw a structure or a molecule. This can be challenging. Right? You do so little practice with Lewis structure that in general, and it doesn't mimic anywhere else in the rest of the semester, that what people will try to teach you is cheats to get through it faster so that they can say that you've learned something or that you can draw a proper structure without actually understanding anything behind it. Why would I get super cranky about that? Drawing structures is what I do for a living in organic chemistry. And if you happen to have to move all the way up to organic chemistry, the very first part, 3 weeks of the freaking semester, I have to double back to Lewis structure and be like, all that crap that someone told you was complete. Thank you. Okay? And how I have to then break you of all of those bad habits. Okay? That's why I get a little bit intense about it, because it ruins what I have to go through and teach for OChem. Okay? So, we will look at both how the textbook presents it, okay, and how I present it. Full disclosure, how I present it will be more work. Okay? It's not that much more work, but it shows the chemistry behind why we're building it, not the answer at the end. Okay? So, Lewis structure. We've got a couple different things that we walk through and do. You've got to calculate your valence electrons. When we're talking about making bonds, we care about the outermost electrons, which means when you look at a formula, you have to say, how many valence electrons? How many things are going to contribute to the bonding picture? This is why it's critical to know our valence electrons and be able to find them quickly. That's why we want to know the numbers off the top and not do electron configurations. Okay? Okay? The dividing by 2, I think, is useless and totally unnecessary. Okay? You then need to pick a central atom. How do you know what the central atom is? Well, these rules aren't very useful. We'll get to that. Okay? You then start to place your other atoms around the outside, and you start placing electrons in pairs. This goes through and says surround the central atom with electron pairs. That's false. It's a bad idea. Okay? We shouldn't be doing that because it, again, breaks the pattern of actual chemical bonding. Okay? Oh, there's the drawing that I don't like. Okay? We're looking at an atom with valence or with electrons around it. This is a horrible, horrible idea. Okay? But what they're trying to walk through is explain these systems and then say, look at how pretty it looks when we actually finally assemble it all together. And it is so bothersome for me that I think I just need to just kind of scroll through it and say, we will come back to it with my slides in a second. Oh God, they're even gonna try resonance that way. Oh, so hard. We'll look at charges. Oh, just keep scrolling. Oh, the pain. Okay, so let's cover some definition stuff. Our covalent compounds, when we talked about bonds, we had covalent, we had ionic, right? You okay with that? Turns out we do have some other kind of categories that come up. We also talked about metallic, and we said, oh, let's just ignore it. That's outside of our scope. We'll also encounter a bond known as a polar covalent bond. Okay? Our covalent bonds have different breakdowns. Okay? So we had HCl, right? We had sodium chloride. And now let's do HO and then kind of ignore the H out there, but I need to include it just kind of for goodness sake. Okay? HCl, we said, was hydrochloric acid, also known as danger. Sodium chloride, we said, was table salt. What kind of bond in HCl? Covalent. What kind of bond in ionic? Cool. So non-metals, metals, cool. We got that classification. Now we move here. H and O with the H out there. So that we had H2O, right? H2O is known as water. Cool. We got that. What kind of bond is here? Covalent. Why is it covalent? These are non-metals. Sweet. Remember, our organization system was to dictate something about the chemistry of those bonds, right? Yeah, we'll stick with it. If we compare this bond to this bond, they're the same. But is your visceral response the same between hydrochloric acid and water? No, they're a little bit different, right? Okay? Like when you go in the shower, if it was spraying hydrochloric acid at you, you would probably have a slightly different response than if it was spraying water. Okay? There's a difference in reactivity. What that's ultimately saying is that we need to differentiate that. We need to call attention to there being a difference there. Okay? It's still a covalent bond, but that covalent bond has a slightly different property that we need to nuance. Polar covalent. Okay? So the polar covalent category is really adding in a new type of category that helps us to explain that yes, it's a covalent bond. Yes, there's technically sharing of electrons, but they aren't being equally shared. That unequal sharing of electrons is what's causing the reactivity that we would associate with it. Okay? That becomes really important when we go through and deal with polarity and separation of charges, which is ultimately what this is going to dig into a little bit. So how do we decide we have a polar covalent bond? Okay? Or an ionic bond? Well, let's define those. How did we know we had an ionic bond?
They're between metals.
Try again. Metal and a non-metal. Here we go. And metal deserves to be in black because like, right? So ionic bond. Thank you. You shouldn't have laughed. Just for the record, I didn't deserve that one. Okay, an ionic bond. Okay, we've got that, and then we also had a covalent bond. Okay, and that was between nonmetals. Okay, and in particular, two nonmetals.
So it's three. That still count?
Say it again.
Is three nonmetals will still count? Or?
Is three nonmetals going to be a bond? Define. You're saying no. You were the first to jump on that. Why is that a no?
Because it's not included with another element.
I don't understand. What are you going to say? What's a bond? Sharing of electrons between two things. So if I have three atoms, HOH, I can reference this bond. I don't care about the other H. Why not?
Because that won't be the bond.
This arrow is referring to this bond, which connects what things? Hydrogen and oxygen. I don't care about that oxygen because that's a different bond. A bond, by definition, will only be two atoms. Your molecule can have tons of bonds. I will only reference one bond at a time. Does that make sense?
Yeah.
So we won't be adding another thing. That's not a bad idea. Try and tweak that. Okay? The polar covalent bond is a new category. Okay? Covalent bonds were equal sharing of electrons. Ionic, totally not sharing electrons. Polar covalent is somewhere in the middle ground. We're sharing, but not really fairly. How do we differentiate that? That compound would technically fit in that category, but we need to figure out what defines our polar covalent. So what things are in our polar covalent compound?
Two non-metals are sharing.
Uh-oh. I already said uh-oh. Because as soon as you say two nonmetals, if we're writing out our definition, nonmetal and nonmetal, what's going to be problematic? That's the exact same definition as our covalent bond, which it is, which means we need a refinement of our definitions. And ultimately what that refinement is going to come back to is we're going to uber define the covalent bond. It's equal sharing of electrons. Well, is there a thing that describes the ability for one atom to share electrons with another atom? Thank you for following the heavy hints. Electronegativity is by definition, right, the ability for one atom to share electrons with another atom. And in particular, it's how much an atom takes electrons from something else. Okay? So a covalent bond was equal sharing. When would I have a covalent bond if we bring in this concept of electronegativity? No. So most electronegative, fluorine. Okay, fluorine is the most electronegative. So if it's the most electronegative, when I bond it to something, what is it going to do to the electrons in that bond? It's going to take them away. Okay. So we put fluorine here and we got a bond to something, we'll just say X. Fluorine, being the most electronegative, is going to suck all the electrons away. Whoop. Well, if it does that, it's now gained electrons. It's starting to become what charge? Why negative? It's taking the electrons. So it has gained electrons, and since electrons are negative, it's starting to become negatively charged. What is our atom X starting to become? Positive, because it's now lost electrons. Awesome. This looks like an ionic bond. I don't want it to be ionic, but I do still want to keep the meaning of the negative and positive. So what do? I invent a new symbol. What is that symbol?
A hanger.
I mean, it does look like that. It's supposed to be a delta symbol, a lowercase delta. If you've seen, harsh. If you've seen a delta, usually means a change. That's what this is trying to imply, is a change in charge. So we could use this delta notation to help dictate that charge. Right? So if we bonded fluorine to anything, it would generate a charge, a partial charge. If it's generating a partial charge, that's not sharing electrons equally, and that would be polar covalent. Everybody okay with that?
So does a polar covalent bond generate as much heat as a covalent bond or ionic bond?
Different amounts of heat. That one I've never quantified to actually think about, and I'm going to say is a distraction from what we need to get through today.
No.
Sorry. All right, so everybody okay with that? Because we put fluorine in there, unequal sharing of electrons. Okay, careful with our notes. Because of course, as we come up with theory, what does your jerk of an instructor, sub-instructor have to do? Of course, I have to break your theory. Instead of being any atom, I want to pick fluorine. What happens when I bond fluorine to fluorine?
They cancel each other out.
Is this red fluorine taking the bonding electrons?
No.
No. Is the green fluorine taking the bonding electrons? No, which means no one's taking the electrons. Which means no partial negatives, which means equal sharing of electrons, which means covalent bond. So it's not just that I have an electronegative element, it's that I have a difference in electronegativity between the atoms in that bond. Okay? That difference can become very challenging to nuance and deal with. Okay? So what we would like to do is have a rule of thumb, right, to help us navigate, where's my pen? This system. That rule of thumb that becomes really important for a covalent bond, okay, is same element, I guess I'll write it, element to same element. So if I bond fluorine to fluorine, that's a covalent bond, or what I would classify as covalent. Okay? We could add the word non-polar because it's not generating those charges. Make sense? I could do carbon to carbon, non-polar covalent. I can do hydrogen to hydrogen, non-polar covalent. Oxygen to oxygen, non-polar covalent. this becomes interesting, and you might have a good memory enough to call me out on my examples, so I appreciate that. Okay? We'll come back to water in a second. Okay? Water, hydrogen to oxygen. That's not same element to same element. Okay? It is a covalent type bond because it's nonmetal to nonmetal, but it is a difference in electronegativity. So the hydrogen to oxygen is actually a polar covalent bond. So I actually picked that as a bad example in comparing it to HCl. Okay? What is sodium to chlorine? What is a covalent bond? Sodium to chlorine. Is that, what kind of bond is that? Is that nonpolar covalent? That's ionic because metal.
Oh, wait, no. Hydrogen and chlorine.
So now hydrogen to chlorine. What categorizes that? Turns out that that is also polar covalent. Well, dang, how am I able to know that that's polar covalent? And H to O is polar covalent. They're not the same. Okay? So because they're not the same, I put them in the polar covalent category.
So it's the difference in electronegativity.
It's ultimately coming down to that difference in electronegativity. Why are ionic bonds ionic? It's not necessarily because they're metals, but if we look at the trends for electronegativity, guess what your metals are? Insanely low, which means when you bond any of the metals to a nonmetal, the nonmetals all have higher electronegativities than the metals. These categories are actually due to calculating a difference between electronegativities. Nobody's going to memorize the electronegativities, which is why we need the rules of thumb. Metal to nonmetal. Nonpolar covalent, same element to same element. Polar covalent would then be what?
Not the same.
Different elements. We could work with that, right? And of course, now that we've got this good theory on what it could be, let's go ahead and break it. Hydrogen to carbon. Those are different elements. Nonpolar covalent. Come up with a rule and then Mike breaks it. Okay, yes. Ultimately, these rules that we're creating here aren't rules, they're guidelines. Okay? There will always be exceptions to the guidelines because they're guidelines. The absolute rule is calculating the difference in electronegativities. Since you will never calculate the difference in electronegativities because you don't know them, that's not a useful rule. Does that make sense? Will you encounter carbon to hydrogen frequently?
Yes.
Yeah, actually, yes. When we talk about bond characteristics and classifying bonds in chemistries, carbon to hydrogen is by definition organic chemistry. Like, I don't have to take organic chemistry, it's okay. Why do we call it organic chemistry?
It has carbon.
Because it has carbon and hydrogen in it. Have you heard of anything being called organic other than just organic chemistry? Is your skin organic?
Yeah.
Is a wood table organic? Is every biological system you've ever talked about organic? Yeah. Okay. Carbon to hydrogen shows up everywhere. So in our rule of thumb, you'll note that I said 1, because guess what rule 2 is? Or guideline 2. Carbon to hydrogen.
So that's the only exception.
Remember,
Or one of the only.
the most common exception.
Okay.
If you know those definitions, right, and we floated over this, we'll come back to that one in a second. If we know those definitions, 99% of the time, you've covered your things. You've covered your bases, and you have your answers for the classifications of the types of bonds.
So why is it a covalent bond? Try like leaning to the right.
This falls down on my head. See? Fine. There's a C and an H down there, just for the record. Okay. Sorry, you said something other than yanking it to the right?
I said, why does it make it a covalent bond and not a covalent?
So nonpolar covalent bonds, these classifications are ultimately the difference in electronegativity. An ionic bond is a huge difference in electronegativity. A nonpolar covalent bond is a small difference in electronegativity.
So there's a small difference in electronegativity.
Then it's by definition nonpolar covalent. But because you don't know the electronegativities, you can't calculate that, so you can't quantify it. That's why you need guidelines. Is there a but? I heard the but.
Yeah.
No.
I'm
Okay.
like looking over here, it's like.
So looking at the periodic table, does the periodic table hold the electronegativities? No. At best, it gives you trends. The trends won't be useful if you need to absolutely quantify. This is why I said knowing ballpark estimates and the big exception to your rule of different elements could help. Different elements is the first time I've ever heard that. I don't know why, but that actually works out better than what I was about to say. Okay. So how do we know we have an ionic bond? And everybody's saying metal and nonmetal. Cool. I would take a step back. Do you need to remember nonmetal? No. When you see an ionic bond, how do you know you have an ionic bond?
It has a metal in it.
It has a metal. Because we don't have metal-metal bonds. We aren't talking about those. So you don't have to worry about that extra part of the definition. Less stuff to memorize. How do you know you have a nonpolar covalent bond? Same element to same element.
Except that are not related metals.
And carbon to hydrogen. They do have to be nonmetals, but do we have metal to metals? No. So this nonmetal to nonmetal, I would argue, we don't really need to talk about, right? We really just need to know same element to same element. Okay? And carbon to hydrogen. The polar covalent would be different elements. The rule that I usually drop for different element or for polar covalent is anything that is not ionic or nonpolar covalent. It's the catch-all bucket that gets everything else. Kinda, sorta? Okay. So cool. That's our electronegativity. Okay. There are trends. The trend is useful to have memorized because it can help you kind of predict things. You will probably see questions on it. Fluorine is your highest. Cesium is your lowest. Okay, as a general trend. If you've got that trend nailed down, you're probably okay for calculating things. You'll notice on this that we don't see any of that entire bottom two rows. Why not? Those are so rare to deal with that we typically don't even see bonds with them, so we don't bother to evaluate their electronegativities. Okay? You'll also notice the entire bottom row, the periodic table being shown here, we haven't evaluated. Why not? Again, they're all man-made, low likelihood. The very last column, we don't see electronegativities. Why not?
Because they're gases.
Oxygen and fluorine, also gases. Why is it being noble gas matter? Electronegativity is talking about what? What electrons? It's not valence. The bonding electrons. What was special about our noble gases? They're perfectly stable, which means, right idea, they're not sharing with anybody, they don't make bonds. So we don't look at their electronegativities because electronegativity by definition is looking at a bond. If they don't make bonds, we don't evaluate it. Simple. Oop, sorry. Okay. Here they're going through and actually calculating differences. That only works if you know the values. So they're looking at electronegativity for hydrogen being 2.1, chlorine being 3.1. We look at that difference. That absolute difference is high enough that it classifies it as a polar covalent bond. Okay? That works. That's the true definition. But since you typically don't know the electronegativities, that's not a useful definition. Make sense? Okay. Delta notation, we already kind of talked about it. Are we okay with that? Their deltas look prettier than my deltas. That's okay. Okay. The point of the delta notation is trying to accent the polarity of your bond. So if I look at that HCl bond, is it ionic? No, because they're all nonmetals. Okay? Is it nonpolar covalent? Is it same to same? Is it hydrogen to carbon? No, which means it's polar covalent. So if I now want to add some information to my bond, I could go through and say this is a polar covalent bond, and I want to be aware of how the electrons in this bond disperse themselves. Okay? Because chlorine is more electronegative than hydrogen, those electrons start to drift towards chlorine a little bit more. Which means hydrogen loses an electron. Well, what happens if I lose a negative charge? I become positively charged. Chlorine, on the other hand, started to gain an electron, which means it becomes negatively charged. As I draw this looks an awful lot like the notation I used for an ionic bond, but it ain't ionic. So I want to call attention to the difference in charges, but I don't want it to be confused with an ionic bond. So I invent a new notation. That new notation is bringing in the delta symbols. So those are just modifying the positive charge to say it's not actually positive, it's only sort of positive. So you can envision the delta as a sort of symbol. Does that help you? You can do more delta notations, nonpolar covalent bonds. We won't see any delta notations because they're equally sharing electrons. So there is no charge imbalance. I'm just going to say you should look at it. I am going to rant here because biologists piss me off about this too. Hydrogen bonds. Okay, we've got a pictogram here, right? Nice little picture. Okay, and if we were to draw this out, really what we're saying is we have H O H H O H H O H, yeah? What are all the black lines? Bonds, do better.
Symbolizing the bonds.
Yeah, they are symbolizing the bond. What kind of bond?
Polar.
They're polar covalent bonds, yes. What are the red dashes?
Those are all somehow connected.
That's some other connection floating out there. Okay? They are not bonds. Okay? Be extra crystal clear on that. Anybody telling you that those little dashes are bonds is wrong. Okay? What are those little dashes called? And this is where it's going to be obnoxious. You're going to be like, but didn't you say you're wrong? Those little dashes are called hydrogen bonds. You said they're not bonds. That's because hydrogen bonds are not bonds. The moron that named it decided to call it bonds. Why? Because they're really, really strong. They are very important to almost everything we would study within biology. Right? So they're incredibly important. So some poor sap looked at it and said, this is such an important thing. I want to give it a name so that everybody acknowledges how important it is. And they called it hydrogen bonding. It is not a chemical bond. It is a very strong attraction between different molecules. That strong attraction is a force. That force will usually get discussed much later in the semester. At least in my class, it's Unit 4, and it's probably the same for Ms. Soos' class too. Okay? But I want to be extra clear here. It is not a bond. You typically see it when you have a hydrogen bonded. So now we're referring to the black lines. When you have a hydrogen bonded to oxygen, nitrogen, or fluorine, you have the potential for these red dashes to appear in a mixture. That's hydrogen bonding. And if you're confused by that, absolutely fair game, you should be confused by it, because we really aren't talking about it appropriately in this context.
So, any bond that has hydrogen is attracted to another bond that has hydrogen in it?
Hydrogen, when it is bonded to oxygen, nitrogen, or fluorine, has the potential to generate hydrogen bonding somewhere else in the system. So it is not any bond to hydrogen. It's only bonds from hydrogen to oxygen, nitrogen, or fluorine. Okay? How do you remember oxygen, nitrogen, and fluorine? There's a couple ways of doing it. You could change the order around. You could say hydrogen just wanted to have some fun. Fluorine, oxygen, nitrogen. Fluorine, oxygen, nitrogen. There it is. Okay? Or you can be like, hydrogen has had enough of Mike's jokes. Nitrogen, oxygen, fluorine. Okay? Only those three atoms have to be bonded to our hydrogen. You're now going to remember it, aren't you? Okay? We get it?
I guess.
So, and it is kind of a weird concept. What we're talking about is that attraction is just really, really, really strong. You just have to know when that attraction exists.
I just call it hydrogen attraction.
Yeah, your philosophical argument, unfortunately, and yes, I completely agree with you. I think it's a stupid name. Yeah. Chemists aren't necessarily smart people, for the record. Particularly old chemists. Okay? The next part is dealing with shapes of molecules. Before we really get into the shapes of molecules, we should look at Lewis structure. And since I glossed over Lewis structure, I'm just going to whip through all that real quickly just to make sure there's nothing at the end of it that we really need to worry about. Chemical bonds. Cool.
Can you take a break in like 5 minutes?
No.
Yeah, let's go.
Yes, absolutely. It's okay. So lecture officially ends, I think, at 11.
At 11. Just push the-
At 11? I mean, you're welcome to get up and leave at any time for a break too. But if like the class is like, no, Mike, you just shut up for a little bit, that's okay too. Do we want a formal break?
I say we just finish. Yeah, just finish.
Sorry, you just lost out. That was 3 people. 3 people said just finish. Okay, so let's take a look. Electronegativity. Ta-da! We talked about that. Okay. Are all bonds the same? No. We have our 3 primary categories: ionic, polar covalent, nonpolar covalent. Okay. This slide has a little bit more context that we didn't get on the others. What is this referencing? Yeah, this is the difference in electronegativity. If I look at a sodium and a chlorine, the difference in electronegativity, if it's larger than 1.7, it is by definition considered ionic. Okay? It just so happens that when I put a metal next to a non-metal, in the vast majority of cases, the difference in electronegativity is larger than 1.7.
Polar covalent is just between 0.5 and...
Yes. Our non-polar covalents, our differences being 0.5. Our polar covalent is anything sitting in the middle. Right? And again, those numbers I don't think are useful for you because it's going to be a very rare scenario where you are actually given the electronegativity values or expected to use them. Okay? So, Lewis structures. Okay? Because I do kind of want to get to some of the nitty-gritty detail here. Lewis built his theory off of cubes. How many points are on a cube? 8. What did we say there was a rule about?
The
Octet. Why did he pick a cube? Because there were 8 points. Right? And so what he started to go through and do was take our valence electrons and put them on the points of that cube. So we go, oh, there's an electron there. And then he went over and looked at the other one. He's like, oh, well, we've got 7 electrons. So that means there's 7 electrons out here. And now if I make a bond, I'm overlapping this face or that line with that line, and I now have a bond. That means when you draw out a Lewis structure, you have to draw cubes for every Blumen atom. That's an appropriate response. That's obnoxious. Okay, we don't want to draw that 3-dimensional thing, particularly because we're looking at a piece of paper which is 2-dimensional. So what's the 2-dimensional form of a cube? A square. So when we're talking about Lewis structure, really what you're doing is picking your atom, and all of your atoms are sitting inside a square. And you are now connecting those squares to other atoms. And how those squares connect is now going to be looking at our electrons and how we place the electrons into that system. Those squares are figments and they do not need to be included. I generally do recommend using squares on the center atom, right, and then ignoring all the others, and we'll see why when we get towards the end. Okay? Periodic table, we need to know our valence electrons. It's a good thing we summarize that, right? We know what our valence electrons are. Yeah. Depending on the periodic table, sometimes you'll see Roman numerals. The Roman numerals are nicer because how many valence electrons are in the first column? 1 or 1. Over here, we said oxygen has number 16 above. Roman numeral? VI for 6. Okay? So our valence electrons are stored on the periodic table. We need that, and we also need to have a basic familiarity with the electronegativity. Okay? I know, we just talked about that. How could you possibly apply it? We give you facts, we try and practice and learn. Okay. These are the rules for Lewis structure. Okay. Step 1, we need to know everything that's going to go into our drawing. What's going into our drawing is the atoms and their valence electrons. Okay. The way I would envision Lewis structures is that we're coming together for a potluck. So we are all bringing food to the party. That's our valence electrons. Okay? All the food comes in, and then we divide up that food accordingly. We'll deal with accordingly in a second. Okay? Depending on the formula, you may see charges. Charges can be counted as extra electrons or less electrons, depending on the charge. We need to choose a central atom as step 2. So what atom is going to be the focal point for that? Okay? So where are we going to have our party? Should we have our party at the introvert's house? No, the introvert probably doesn't want anybody in their freaking house. We're going to pick the one that is most willing to interact with everybody. Okay? Well, what is that interaction? That's our electronegativity. The more electronegative, the more it's holding its electrons. It doesn't want to share. So our higher electronegativity is effectively an introvert. Don't put that in the middle. That pisses off the introverts. Okay? Put them on the outside.
I mean, not like oxygen would be more like extra electricity.
Oxygen, according to our trend, is very electronegative. We would expect it to be on the outside. And in the vast majority of scenarios, it is. There are some scenarios where it doesn't. That's dealing with our exceptions. Okay? The center atom must be able to bridge. Okay? The center atom has to form a bond on one side and a bond on the other. Hydrogen can only form one bond. So if I were to look at, say, the compound of H2O, when we draw that out, we put oxygen in the middle. Oxygen is electronegative. Shouldn't it not be in the middle? Hydrogen can't be in the middle because it can't bridge those two other sides. Does that make sense? Okay. Here's the big one that I would argue is the biggest shift away from most methods that I've seen. It's right here in step 3. We will place our electrons on the most electronegative element. Okay? So let's use our potluck example. Okay? It gets a little bit mean. We're now adding electronegativities to all of our guests. That electronegativity is how mean, nasty, evil they are that they're going to get food first. Okay? That's our electronegativity. Okay? So that oxygen that we placed on the outside may not want to share with anybody. Okay? They're going to go through and get their electrons first. We're not placing them anywhere else. We want to go satisfy them first, and then we'll worry about everybody else. Well, what's satisfied? Satisfied is our octet. So we want 8 electrons around those electronegative elements. Then we continue to add electrons to the rest of our atoms until we've put in all of that total that we counted at the beginning. Okay? If we're lucky, we're effectively done at this point. If we're not lucky, we have some other things to do. Okay? Minimal one, anywhere I have pairs of electrons between atoms, I will convert into a line. It needs to represent a bond connecting those atoms. We want that, and we'll need that later on, because it helps us to understand that we're actually sharing electrons through that space. Rule 6 is the killer. 6 and 1. Move non-bonding pairs of electrons between atoms that have not satisfied their octet. Okay? This is a challenging one, and we'll look at examples. Okay? Kind of a subset of Rule 6. If there were multiple ways to do step 6, that's resonance. Okay? And depending on how you dictate and look at things, that may mean for an individual formula, you have to draw 6 structures. Because not one of them is correct. All of them must together be correct. Okay? And then the last one, generally easy and almost always forgotten, assign your non-zero formal charge in the upper right-hand corner. Okay? Relatively straightforward for Chem 130. You just have to say that it's charged, and that's about it. Okay? We ready for some examples? Cool. We already know what H2O looks like, but we'll go through and do it anyway. Total or valence electrons. Hydrogen comes in with how many valence electrons? Looking at the periodic table is useful. In theory, you would have had it memorized. 1, but it says H2. What does that 2 mean?
There's 2 of them.
2 hydrogens, which means multiply it by 2. What's 1 times 2? 2. Oxygen comes in with how many valence electrons?
8 or 6.
Okay, then this becomes a challenge. We have to make sure our valence is stored across the top. Oxygen has 8 total electrons, only 6 of them matter. We now total it up. 6 and 2 is 8. I now move to step 2. I want a central atom, the least electronegative. So awesome, we had our electronegativity trends memorized. We go, oxygen's the most electronegative. I don't want oxygen, I want hydrogen to be my center atom. I would then scatter my other atoms around on the outside of it. The problem with this is that hydrogen can't bridge the other hydrogen and the oxygen, which means that doesn't work. Our center atom must be able to bridge. So even though oxygen doesn't want to be the center atom, it doesn't have a choice in this scenario. It has to be the center atom.
And how do you know if an element can bridge or not? Is there really no simple answer?
Hydrogen can't bridge, and our halogens, for the most part, can't bridge.
Which do you think is better?
Oxygen can bridge, nitrogen can bridge, and then our halogens can't. Okay. And there's exceptions to that one too, which is why I'm not happy with the answer I'm trying to give you.
But wait, isn't oxygen pretty much want to bond?
Yes. Or it will make bonds with anything. Yes. Because what it's trying to do, because it's so electronegative, is suck electrons in. This is why if we look at oxygen gas, it tends to be very reactive, because that's oxygen bonded with oxygen. It can't steal electrons from something that's equally strong as it. So what does it do? Forms a bond to something else that it can steal electrons from.
So how come it doesn't want to be middle, essentially, with hydrogen?
Because hydrogen doesn't have the ability to share both directions.
No, I'm
So
saying why doesn't it? Oxygen.
with hydrogen, it does. In other cases, if we put it in the middle, you're now sharing. And we'll look at a different case we'll accent that. We can't do that with the next one that's up there, but we'll call it out. It now says add electrons to the most electronegative. Which element is the most electronegative? Oxygen. I want to place those electrons around the oxygen in pairs to the center atom, okay, or to our oxygen in this case, because it's the most electronegative, and I want to place those on pairs on the faces of an imaginary square. If you don't have a good imagination, that's okay. Draw a box. There's the faces of my square. Start placing electrons. 2, 4, 6, 8. I'm going to place them until I achieve the octet. The octet is 8 electrons. There we go.
Not to do that, though.
Say that again?
You just tell us not to do that.
What did I tell you not to do?
That, right? The diagram of the dots.
I told you not to do the dots for an atom. Is this an atom?
Oh, no.
Nope, it's a molecule. That's the big difference. Okay? And I don't really want to show you what I mean by the other example, but I will do it, just so that you see kind of the contrast. Okay? We'll now continue to add electrons until we've achieved our total. Have we achieved our total? Yes. Everywhere we have pairs of electrons into a line between atoms. This is the abbreviated rules. Okay? So I have a pair of electrons between the hydrogen and the oxygen on that face. So what do I make it? A line. So I would erase, make it a line now showing that bond. Erase, make it a line showing that bond. So far, so good? Satisfy octet. Okay, to satisfy octets, we have to check octets. How many electrons around the oxygen? 2, 4, 6, 8. All 8 of those electrons are around the oxygen. How many electrons around the hydrogen? 2. The line is 2 electrons. We're not splitting the line up. That line is sharing. They're equally accessible. Okay? Shouldn't hydrogen have 8 electrons? No, it's our exception to the octet. Hydrogen only has 2 electrons. Okay? So we've achieved the octet on this hydrogen. We've achieved the octet on that oxygen. We've achieved the octet on that hydrogen. What does that mean? There's no need to move electrons. There is no need for resonance. Okay? This formal charge thing we should technically do. This is a calculation. You don't need to do the calculation, I believe. You should check with your instructor to make sure. But what you would do is if this molecule was charged, you would put brackets around it and you would specify the charge in the upper right-hand corner. Since it is not charged, putting all that information would be wrong. Kind of, sort of? Okay. Should we make a more challenging one? Or you can get a picture, that's fine. What? More? H2CO. We'll make it a whole lot more complicated. Okay? So, step 1, valence electrons. Hydrogen has how many valence electrons? 1, but there's 2 of them, so we multiply by 2. Carbon has how many valence electrons? 4. Oxygen has how many valence electrons? I was about to write oxygen again. 4 plus 6 is 10 plus 2 is 12, and we now go through. We've got 12 total valence electrons that we're allowed to put into this. I need to pick a central atom. The central atom should be the least electronegative. Hydrogen is the least electronegative, okay, but it can't bridge, so it doesn't work. So now we're between carbon and oxygen. Carbon is less electronegative than oxygen, so our center atom becomes carbon. Awesome. I will now scatter the rest of my atoms around my central atom. Okay? Note that again, I've placed those atoms kind of on the face of a square, okay, around the central atom. I now want to go through and add electrons to the most electronegative. Which element is the most electronegative? Electronegativity trend. Which element is the most electronegative?
Fluorine.
Fluorine. Which element is closest to fluorine? Oxygen, carbon, or hydrogen? Oxygen. Oxygen is the second most electronegative element, which means our electrons need to go on the oxygen. 2, 4, 6, 8. Everybody see that I'm also placing those electrons effectively around an invisible square on that oxygen. Okay? I'm not squaring the oxygen because the center atom becomes the important one, which we'll address in a little bit. I have 8 electrons shown. How many electrons do I need? 12, so I have to put in more electrons. I'm going to continue placing those electrons on the next most electronegative element. What's the next most electronegative element? Carbon. I'm going to go through and place those electrons where there aren't already electrons. Because remember, electrons want to repel away from each other. Okay? I could do this. Okay? Why is this problematic?
Now you have nothing to bond with.
There's no bond that I could put in there. Everybody see that? So when I'm placing those extra electrons, I typically want to start placing them where I know I want a bond. Okay? That way I don't miscount something. So we'll place there. How many electrons are now present? 12. How many did I need? 12. So I'm now done. Everywhere I have a pair of electrons, between atoms I can turn into a line. 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 Everybody see it? Cool. What's the next step? Satisfy octets. To satisfy octets, we have to check octets. How many electrons around the hydrogen? 2. How many is it supposed to have? 2. So hydrogen's fine. How many electrons around the oxygen?
8.
2, 4, 6. Line is 2 electrons. 8 electrons around the oxygen. Satisfied. Hydrogen. 2. Carbon. 6. Missing its octet. Okay? That means I have to do rule 6. I have to move pairs of electrons. The question becomes how I do that. So, first thing to be aware of, there's a big mistake that commonly students will do. They'll go, ta-da, it has its octet. Why is that a problem? I'm only allowed 12 electrons. I just added 2 more. I'm now at 14 electrons. I'm not allowed to do that. Okay? That was the point of totaling the valence electrons.
So can we take away 2 from oxygen and add it to carbon?
Cool, let's take away 2 from oxygen, and let's put those 2 on the carbon. Because that's now, shush. Satisfy the octet by moving pairs. Okay? What did you do? You had 2 electrons on the oxygen, and you moved them to the carbon. You have satisfied exactly what I'm asking you to do. Perfectly valid conclusion. Check your octets. Does carbon have 8 electrons?
Yeah.
Yes. Does hydrogen?
It has its 2.
It has its 2. Hydrogen?
6.
6. Your move satisfied one problem but made another. Okay? So where can I move that pair of electrons so that I don't ruin oxygen's octet but also allow carbon to gain an octet?
Take 1 from each hydrogen.
Then I don't have a bond and hydrogen loses and only has 1 electron. Okay? That your statement was also take 1 electron. What does this say? Moving pairs. So you're breaking my rules. And not in a way that invalidates my rules, you're just not following them.
Would it be a double bond between oxygen and carbon?
Change your wording.
Would you add another line? I don't know the reason.
No. If I add another line, let's do that. Let's just say, run to the letter of what you just said.
Yeah.
Does carbon have its octet? 2, 4, line is 6, line is 8. Does carbon have its octet? Yes. To the letter of your statement,
Yeah.
Now
okay, now the oxygen has 10. That's no longer octet. And to the letter of your statement, 2, 4, 6, 8, 10, 12, 14. How many electrons? Fix your statement. Absolute right idea, just wrong implementation. Can you fix it?
I don't think so. All right.
I don't know.
What does the rule tell you to do? Move a pair of electrons.
Yeah, if we can't, we go to step 1.
No, move a pair of electrons. You tried moving a pair of electrons from the oxygen, giving them to the carbon. You caused another problem. You tried adding more electrons. Can't do that. That's not moving a pair of electrons. Where can I move a pair of electrons that both oxygen and carbon have access?
to a hydrogen.
No. No.
Would it be like on the inner shells? No.
Let's just pretend you said, can you just move it to the inner? How about I just move that pair of electrons to the space between the oxygen and the carbon?
Oh.
I didn't know you could do that.
Did I say you couldn't do it? How did we get the line between the carbon and the hydrogen?
There's 2.
2 electrons between the atoms. We're allowed to put 2 electrons between atoms. That's perfectly acceptable. I want to move that pair of electrons to a space where both oxygen and carbon have access. Where do they have access? In the space between them. That notation looks a bit silly. That's because I have 2 electrons between atoms, which means
They're both
convert into a line. This is why I said you were darn close.
Yeah.
Okay? What do we now have between the oxygen and the carbon? We have 2 lines. We have a double bond. That's where double bonds come from. We don't just say, oh, I want a double bond. They come into existence because we're trying to satisfy octets. That's where they come from. That's amazing. Stupid, silly little theory, and it does a phenomenal job predicting that. That's crazy. Okay? It takes practice to manipulate. Okay? Follow the rule set. Okay? I have access to the course. I will post these slides so you've got access to them. Okay? I'll link to them, and I will also post the video recordings. There'll be 2 of them. 2 freaking 1 hour long videos, but if you want to watch them again, just double time. It gets more exciting that way. Okay? And you can review through to find the content that you need to help work through it. Kind of, sort of? Okay. Let's see. We decided it was officially 11 is when we need it?
Yeah.
Yeah? Okay. Just wanted to see how far I wanted to get. We're going to address a couple things. First, we're going to do another example. This one is going to be a little bit harder. Different elements, bigger elements, and charged. Make life miserable, right? Okay. So how do we do it? Total valence electrons. How many valence electrons does sulfur have? 6. How many electrons does oxygen have? 6. There's 3 of them, so multiply by 3. What's 6 times 3? 18. Dang, fast math. Charge. Charge is now appearing. We do have to worry about it here. It says -2. How do I become negative charge? What subatomic particle is negative? A neutron is neutral, so no, it is not negative. What's that?
Electrons.
Electrons. Okay? Electrons are negatively charged. If I have a -2, what does that mean happened? I've gained electrons. How many electrons did I gain?
6.
2, because it is a 2 charge. Okay? The 6 is looking at the valence electrons for each of those elements. That -2 just says I have 2 extra electrons. What am I counting? Electrons, which means the charge means what do I have to do? Add 2 more electrons. 2 and 18 is 20, and 6 is 26. We get 26 electrons to go into our drawing. We've got our sulfur. Put my box on it. My oxygens. Oxygen, oxygen, oxygen. We'll place our electrons in pairs to the most electronegative. That would be our oxygen. Does it matter which oxygen we start with? Nope. Next oxygen. Pairs. Pairs. Okay, how many electrons have I drawn? 8 times 3, 24. I need 26. What do I need? 2 more electrons. Only place I can place them is now on the sulfur. Anywhere I have a pair of electrons between atoms, I will turn into a line representing the bond that connects those atoms. Okay? Satisfy octet. How many electrons are on the oxygen? 2, 4, 6, 8. Oxygen.
8.
2, 4, 6, 8. Oxygen.
8.
2, 4, 6, 8. Sulfur.
8.
8. What does that mean?
6, please.
Everything's satisfied. My God, I don't have to move electrons. Yes! Okay? What does that mean? Oop, last step. It's only crossed out because this is a calculation. You don't need to run the calculation, but we do need to specify the formal charge. This molecule we know was formally charged because it was written in the upper right-hand corner. So what we would do is put brackets around this, and we would say -2. That's it. What we've now drawn is the Lewis structure for SO3 -2. Okay? fun, exciting thing. Anybody with a computer, look up formal or Lewis structure SO3 minus 2. Try it this way. Look up sulfite. SULFITE. Lewis structure sulfite. Come on, internet, work faster.
Like this?
Yep. Does my drawing look the same as the drawing that's on the screen? No, it's not. Why not? Because of a bunch of rules you don't understand because you are not in an advanced chemistry class. Be careful looking up answers online. Okay? You need to understand this rule set. This rule set will get you to the proper answers. If you just Google them, there's a high likelihood that you will be drawing the wrong answer. Make sense? Okay. We'll do it again, except this time we're changing it up. It's no longer sulfite, it's sulfur trioxide. Why did the name change? There's no charge. As soon as we drop that charge, we have to worry about that. Sulfur has how many electrons? 6. Oxygen has how many electrons? 6 times 3 equals 18. We total it up. What do we get? 24. We draw it out. Sulfur. Oxygen, oxygen, oxygen. Whoops. We draw our box around our sulfur because Mike likes being repetitive. 2, 4, 6, 8. 2, 4, 6, 8. 2, 4, 6, 8. Who do we appreciate? Chemistry. Yay! Everywhere there's a pair of electrons between atoms, we turn it into a line representing a bond, 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 bond. We had 24 electrons, right? Are there 24 electrons in our drawing?
Yes.
Yes. Do all of our atoms have octets?
No.
No. The sulfur is missing its octet. So what do?
Take 2 from one of them.
We'll just,
A double one.
we take those electrons and we move them in to make a double bond. Does everybody agree? I don't. Why am I now wrong in blue? Because you all seem to be super happy with our colorful one. Why is mine wrong in blue? What's that?
Does that mean they're all sharing an extra 2?
Does this mean that each of those oxygens could have provided the electrons to that sulfur? Yes. That's resonance. Resonance is saying when I got to that spot where I'm like, how do I satisfy the octet? Is there more than one way to satisfy the octet? That's resonance. Resonance then says that I have to show all of the ways that would have allowed me to satisfy the octet.
So you just have to take all.
So we have to turn them all into double bonds. So that statement, when you say that, is usually what I would say results in this structure. In green, why is green wrong? That should still be 24 electrons. So
Well, because now it has.
yeah, which is probably your refining statement. In green, we still have 24 electrons, but I've exceeded the octet of the sulfur. Can't do that. So that's why the green one is bad. So I have to use the 3 down below. What is the difference between those 3 structures? And this becomes the challenging kind of concept with resonance, right? Is we could have turned those, right? Aren't they all identical? That's kind of the point of resonance, right? They are all identical, except they're different oxygens contributing that charge, right? So when we think about resonance, if you've been in a biology class or heard about dissections, right? Like you pin down the thing so that it doesn't move on you. When we do resonance, that structure is now pinned, right? If there were multiple ways to move electrons, those are unique ways. Those need to get shown. That's resonance. Kind of, sort of? You would have to write all the ways, okay? And for all the ways, there's 3, okay? from an individual oxygen, it doesn't matter where I'm placing the electrons on that oxygen. Right? So it's not like I get a new structure if I use that pi bond, or use, those electrons to make the double bond. Okay? It would still be making the same connectivity between the oxygen and the sulfur. Kind of, sort of? Okay. Extremely challenging concept. Right? It is one that plagues people that have to deal with organic chemistry, which is why we introduce it now so that you're at least somewhat familiar with it and how it comes about. It's the satisfaction of the octet. Kind of, sort of? Sort of, kind of. Okay. I know I'm out of time, but we need this. What you will end up doing once you've drawn a Lewis structure is that we then want to discuss its shape. And a lot of what today's lab is going to look at is some of that shape stuff, so we can set up some of that context. So if we looked at our Lewis structure for water, right? There's our Lewis structure for water. You'll note that when I've been drawing water, and you may have seen elsewhere, the upper right-hand corner, something more like that. What is the difference between my right-hand structure and my left-hand structure?
You put the two electrons on top and the hydrogen down.
Why does that matter? Does that matter?
No.
Right? What we have on the left is ultimately Lewis structure. What we have on the right is an interpretation of Lewis structure according to shape. So what we start with is our Lewis structure. Okay? And again, we focus on our center atom. Look at each face of that square and ask the question, are there electrons? So are there electrons on the bottom face? Are there electrons on the left face? Top face, right face. How many faces have electrons? 4. So we'd move through our thing to electron groups. There are 4. If I have 4 groups of electrons, I call that shape tetrahedral. Right? That's what the chart is supposed to do. It's evaluating your Lewis structure to decide a name.
But the one on the right would have 3.
What's that?
The one on the right would have 3.
Does the one on the right have 3? The one on the right is more of a twisted Lewis structure. If we drew our square, it's there. How many faces have electrons? It's still 4. It's still tetrahedral. So why is the one on the right typically drawn, but the one on the left not? Okay? What we've drawn is the electron group geometry. We just said there's electrons there. What we didn't evaluate is the difference between bonding electrons and non-bonding electrons. Okay? Said another way, if I have $100 in my wallet, okay, I own that $100. But if I'm sharing that with you, do I actually have $100 anymore? No. That money is effectively being shared in different locations. If it's in my wallet, I own it, it's here. If I'm sharing it, that $100 is now kind of floating out away from me. That's changing the shape of kind of the money dynamic within the room. What we're now moving to is not just raw electron groups, but now saying how is that money being dispersed? That's looking at bonding groups versus non-bonding groups. Well, how do we know we have a bond? How do I know how many bonds do I have here? Let's try that. 2. Okay, how do I know I have a bond? Because you told me there's 2 bonds. So how did you get that answer? The line between them represents a bond. So there's 2 bonds. How many non-bonding groups are there? 2. Again, 2 because they're dots, not lines. That's why our notation helps us to differentiate and see that. The notation can guide us. So when we look at it, we're still tetrahedral, but we have 2 bonding groups, 2 non-bonding groups. This changes my interpretation of the molecule, because now I'm saying they aren't all the same electrons. Some of them are different than others. That difference I signify with a new shape. I would call that shape bent, and I would call that orientation of those 3 atoms bent. That one I'd call linear. Okay? Lewis structure doesn't show you shape. I can draw water in a bunch of different ways that looks bent or linear. It's only once I layer in this shape summary do I get the molecular shape. So why would I preference to draw things like this instead of like that? This shows me the actual shape better than that one does. Kind of, sort of?
Yeah.
Okay. If you drew the iPad right now, what does it look like? Straight line, right? Is it a straight line anymore? No, it's a box. Okay? What we're trying to represent is a three-dimensional object in a two-dimensional space. It's very challenging to nuance that. That's why we need different rule sets. So you have to draw Lewis structure first, then you interpret the Lewis structure, both as an electron group summary and as a molecular shape summary. Kind of, sort of? We'll talk about that more in lab, so I'm going to stop for the moment.